So the first session is on the introduction side. So why graphs? Right? So graphs are, very general language for describing and analyzing the entities with the relations and interactions. Right? So sometimes I'm feeling like when we are doing the supervised learning or unsupervised learning, right? So sometimes there's a basic assumption like all the samples are independently distributed, right? Or maybe they don't have, much connections in between, or that relationship is missed during the modeling, right? But graphs kind of put all these entities and nodes together and take advantages of this relationship. So this is an example of graph, right? Say these are the nodes of the graph. So you can think of the nodes as say us humans, right? So each of it can be one person, or each of it can represent one place. Any definition of node you can think of, right? And then we make connections between the nodes. For example, in this group, all the attendees of right now at this Zoom meeting are connected with edges, right? So that kind of, we are all connected by the edges in the graphs. So that is basically what graph looks like. And actually there are many kinds of graphs in real world, right? So say the event graph. So this example shows actually the event of flight. So some flight got canceled because of what? Maybe because of weather. And some flight like is from this airport and goes to another airport, right? It tells you the event around the flight. And we also have computer networks, right? So the cell phones, laptops, servers are connected. And also the disease pathways. So we have attendees from the healthcare industry, right? So the disease pathways that kind of tells you the interactions of proteins. And sometimes when the proteins, so sometimes the disease can be defined by the interactions of, the proteins that behave abnormally. And also we can describe the food webs of birds, right? For example, here, like which bird is fed on what kind of fish, etc. And we can describe the relationship of the species with the webs. And also these particle networks kind of describe the physical laws and forces and how the physical system can evolve. And we have this subways or the bus traffic system that is natural graphs or networks. There are also many like virtual graphs, right? Just social networks, just as us. The Houston Machine Learning Meetup or San Diego Machine Learning Meetups are kind of one community in the big learning world, right? So we are connected by common interest. There are also economic networks showing how the business entities, say the companies and big banks are related to each other. And these communication networks show how people communicate each other, like what's the direct report, or maybe your manager, right? So how the people are connected at the company. And also the citation network. So it's about the publications, the papers, say the news, right? So it's how they are cited each other, right? So sometimes when we see a news, you can see that that news has a link to some other news, right? So it's connected by the links. And also we have a really large internet. It's a graph. So everyone is connected on the internet, by different servers, and I think there will be region servers, and also within a company they have servers, and then these servers are also in some way connected. Right? So it's a really complicated and massive graphs. And also in our brain, we have a network of neurons, which leads to deep learning is another network to model the networks of neurons. And we also use graph to describe our knowledge, such as the knowledge graphs. So knowledge graph tries to map everything we know in the world in a graph. So each node can represent a concept, right? Can be a person, can be a place, can be an event. And then how these entities are related to each other, right? Say, yes, I think this is about the movies, right? So the movie categories and who is start in that movie. And then this also from biological networks, the regulatory networks. The scene graphs is also how you can describe this picture, right? From bottle elements, the shapes, the colors to gradually up to a scene of the photography or picture. And we also use graph to describe our coding structure, right? So how this function is calling another function, right? To show, the structure of your codes. And also the molecules are natural graphs. The atoms and the bonds, right? That defines your molecules. And the molecules again interact to form other shapes of more complicated graph structures, such as proteins, right? And then the 3D shape can be also modeled as graphs, right? So you can think of the 3D shape. There are lots of nodes, right? That stays on the surface, and then the nodes, nearby nodes, are connected together, and they define this 3D shape in the 3D space, of course. So these are, many applications of graphs, and lots of knowledge can be represented in graphs. So the main question is, how do we take advantage of relational structures for better prediction?
How was lunch?
Yeah, how is the lunch is also another main question for this. So we see that there are many complex domains, and they all have very rich relational structures, and it can be presented as relational graphs. And by explicitly modeling this relationship, we can achieve much better performance. And regarding the deep learning toolbox or model deep learning that we kind of get used to or familiar with, is kind of they are all work on more structured input. Although I believe image and text and speech is unstructured comparing to tabular tables, but in terms of the shape, they are kind of structured, such as images are the pixels are laid out in a grid, right? So you can know the size of the grids, for example, right? So it's very structured format of the nodes. And also for the text and speeches, they are a sequence. Right? So each of the words or the audio signals, so you can lay them out like just one dimensional, right? And then you can use convolutional neural network or LSTM to model them. So all the previous deep learning models that we have talked about is designed for sequences and grids, right? So to deal with the images, to deal with text or the audio signals. So right now, just as all these applications that I've shown, examples that I've shown earlier, not everything can be represented as a sequence or a grid, right? And they have, it's very hard to tell what exactly, structures of that graph is, right? It's not a sequence or grid. So how can we develop neural networks that are much more I think I'm off. Let me share the screen again. Okay, so the question is, how can we develop the neural networks that are much more broadly applicable, not just to sequence or grids, right? And it's actually a very active frontiers of machine learning research. So this Stanford course is mainly about graphs, right? So it's a new frontier of deep learning, and the graphs is basically just connect things. And we need, when we do the modeling, we need to take advantage of these connections and the relationships. And here it shows how popular graph neural network grows over years from 2018 to 20. So you see the keywords growth just explode there. So it gains more and more interest in the research field. And also I just searched the 2021 keyword. So this is just a keyword ranking. So in addition to deep learning and reinforcement learning is just very general kind of keywords. You see the COM-service representation learning, I believe it can be also applied to graphs. And also graph neural network comes at the top. Yeah, so definitely the graph neural network is one of the hottest fields in machine learning. And why is graph deep learning hard, right? Because, well, it can have arbitrary size and it can have very complicated topological structures, right? So you see these graphs, well, you can describe the size about how many nodes or how many edges of the graphs, right? That kind of describe the size, but how can you describe about the structure? It's very hard to describe comparing to the images or text, right? So it's a grids of pixels or a sequence of words. And also there's really no fixed ordering in the graph and also no reference point. It is dynamic because the graph can grow or shrink, right? So it can change easily over time. And it has multimodal features. So multimodal features means it can have various data types. So each node can be different type of nodes that it can have different properties. It can come in different shapes. So for example, this node may be an image or another node may be audio. And this node can be just a person, right? So all of these nodes can have different properties or definitions of the nodes. So you see it's a very challenging problem of how can you take advantage of all these nodes, different features, properties, and also at the same time consider their connections in your modeling work. Okay. So what is the graph modeling? So the input will be a graph or a network. And then it will, through some machine learning modeling process. So here it just shows a graph convolution and pass through some functions. And in the end, what we are trying to predict is the node labels, right? Such as the classifier labels that you want to classifying the nodes. And it can be the node labels or to predict new links. And also you can even generate new graphs or subgraphs. So we are going to see more examples like this in the following slides.
Hey, Yan, can I insert a comment here?
Yeah, sure.
So before we had CNNs and the explosion in computer vision, there were a lot of people researching computer vision, and it was mostly with sort of these handcrafted features that people were trying to do to extract the meaning of images. And if you look at like natural language processing, right, there's a lot of understanding. People try to have handcrafted grammars and things like that. And what we've seen is the power of, if you can train a complex, a deep neural network model, then it can learn these features, right? Instead of using just the handcrafted ones. So I think what's exciting is that that graph learning right now might be kind of at sort of like the AlexNet moment that we saw for computer vision, where people are figuring out ways to build deep neural networks, and we're just going to see an explosion of improvement in what models can do. So I know you're already headed there, but I just thought that it'd be useful to sort of compare it to some of the things that we've seen with vision and with NLP.
Yeah, so I think it all comes, I believe, no matter it's images or a text or graphs, they all come from the traditional world. Well, every time we design the features, right? So for graphs, you can also design the features based on the nodes, and also you can try to define whether the graph is central or not, whether there are several hubs, right? So you can extract all those kind of features. But I think what's more powerful is this, such as the deep learning always tries to model from end to end, right? And you can directly learn the features automatically, and that will be directly taken in or integrated into the model by itself. Yeah, I think that's the most powerful part of the representation learning. And as you see from the previous keyword ranking, representation learning is always the top topics for the machine learning research, definitely as well. Yeah, so here is just an example of what is the representation learning, right? So you have the node, you can be just an index of the node, and representation learning is to learn a vector representation of the nodes so that similar nodes in the network will be embedded close together, right? So if these two nodes kind of close or similar in a network, then their vectors will be similar, or their distance between these two vectors will be close in their embedding space. So that's about representation learning.